let's also see if there's a way that we can use UV-Vis data to understand the electronic structure of the complexes that we made in the lab. Let's go again to our tetrahedral iron 2 complex. That's a D6 iron 2. And this is in technically the low spin configuration. There's also a high spin configuration where one of the electrons in the bottom goes up to the top. More on that in lecture. But for now, we can think about this particular complex and consider what the UV-Vis spectrum of something like this should look like. So when we do a UV-Vis spectrum, we have our light source. And that shines on our sample. And our sample, depending on what is in there, is going to absorb a certain amount of wavelength. So we have an incident radiation, and we have a radiation that is transmitted, and we have some that is absorbed. So I0 minus IT should equal IA. And that hits our detector over here, which gives us some value of absorbance. The absorbance is how much of our light got absorbed. And that absorbance is dependent on the electronic structure of our molecule. You might hear this called the electronic absorption spectroscopy. That's what we're doing with our UV-Vis. So the thing that causes absorption of that wavelength of light is when the proper wavelength hits the sample to promote an electron from the bottom row up to the top row. Remember, these are our frontier orbitals. We have our HOMO and our LUMO. And what we'll see is when we have an incident photon with the proper wavelength of light, the proper energy, you can convert and have it be the proper wavelength of light, we'll see the promotion of one electron from our bottom row up here to our top row. And we can look at a few different possibilities on how that works, and that's going to correlate to the molar absorptivity, or that epsilon value from our Beer's law. So if you remember over here, we have an absorbance that is equal to epsilon times path length times concentration. That epsilon value, which you're supposed to calculate for your data, because you know the concentration, you know the path length, and you know the value of A that you get off of the spectrometer, that is going to tell you something about how likely a complex is to accept an electron at certain wavelengths. So the wavelength that you need correlates directly to the energy difference between the two orbitals. Okay, so this has to do with the wavelength of light, or the frequency of light absorbed, right? The energy difference between the two states tells us the energy of light that's going to be absorbed. These are all quantum states, and that absorption of light is quantized, but when you put them into environments with temperature, you spread that out and get a Gaussian curve because of that. But ultimately, the peak wavelength that you see is going to be shifting around, and that is going to be the thing that's most related to the difference in energy between these two. That energy is going to be different depending on the identity of the metal ion, the oxidation state of the metal ion, and several other things. The epsilon value of that peak, okay, is going to have to do with our selection rules. So this is the likelihood of transmission. The likelihood of absorption. I spelled it wrong. There's no B. All right. Epsilon is, and I'll use my little proportional to. It's proportional to the likelihood of absorption. It is not exactly the likelihood of absorption. And that's based on two important factors. The first factor is it spin allowed? There's a spin selection rule. Okay, and that is overall the number of unpaired electrons, the number of up spins and the number of down spins must not change. So if we look for this transition that I've illustrated up here, on the before transition, I see 1, 2, 3, 4 up and 2 down spins. 1, 2, 3, 4, 5 up and 1 down. I goofed that up. That is not a spin allowed transition. However, we can do a spin allowed transition if I hadn't accidentally flipped my spin there. This should be a down spin. Now I have 1, 2, 3, 4 up, 1, 2, 3, 4 up, and 1, 2 down, 1, 2 down. That's a spin allowed transition because the spins the overall spin of the molecule doesn't change. So the concise way to put that is delta capital S equals 0. You have to remember that that capital S value is the maximum sum of all the individual m sub s values of the electrons. Remembering that m sub s can take either plus 1/2 or minus 1/2, whether it's spin up or spin down. So if we were to calculate S for both of these states, we would get 1/2, 1, 1.5, 2, minus 1/2, minus another 1/2. This is S equals 1 on that side. Here we have 1, 2, 3, 4 up. That's 4 times 1/2. That's plus 2. 2 down. That's 2 times minus 1/2, minus 1. Again, S equals 1 on both cases. That's our spin selection rule. That's our strongest rule. So things that are spin forbidden have very low epsilon values, somewhere between 1 and 100 per molar per centimeter. Remember, that's our unit for molar absorptivity, so that we can cancel out the units and our path length and our concentration per molar per centimeter. For a spin forbidden complex, we'll always have a very low epsilon. Anything spin allowed is going to be above 100, and there's another selection rule that tells us what the value is going to be after that. That's going to be our Laporte selection rule. Okay, and our Laporte selection rule tells us that the parity of our orbitals in a transition should not change, or must change. So, in other words, we have to go from a Gerada to an Ungerada, G to a U orbital, or a U to a G orbital. Those transitions are allowed. Laporte forbidden transitions are G to G or U to U. Now, if you remember all the way back to how to do this, in a certain point group, you can look on the character table on the quadratic equations and find each of your d orbitals and see whether it's Gerada or Ungerada, right? Turns out all d orbitals are Ungerada. You can do an inversion center on them. Sorry, they're even, they're Gerada, right? Let's take one example, the dxy orbital. If I put that through an inversion center, I get exactly the same thing back. That is a Gerada orbital. That would get a G. But if I'm transitioning my electron from a d orbital to a different d orbital, that's a G to G transition. That is Laporte forbidden. That gives us another rule to go by. Laporte forbidden would be about around, the order of magnitude is about 100 per molar per centimeter. Okay, we might also have transitions that are Laporte, what we'll call relaxed, because if your molecule is in a point group that does not have an inversion center, we don't assign whether it's Gerada or Ungerada. And in the same way, we can mix our p orbitals into our d orbitals. It's an orbital mixing effect that allows us to relax this selection rule. And so for something that's doing a d to d transition in, say, a tetrahedral environment, that one's highly relevant here. You might look up C4V or D4H. D4H is your square planar point group, and TD is your tetrahedral point group. Compare the two on the character table, and you'll see one has G's and U's, the other one does not. That's pretty relevant to what we're trying to do here. A Laporte relaxed transition will be about 1,000 to 10,000 wave numbers. Sorry, per molar per centimeter. And then there's another category where you see very, very high values of that. But that's not relevant now, so I won't go over it. So this is how we can take our UV-Vis data and better understand the transitions that we're seeing. Once we've thought about the proper d electron count, the possible geometries, tetrahedral or square planar, populated them with our d electrons, we can then think about whether that transition should be spin allowed or spin forbidden, Laporte allowed or Laporte forbidden or Laporte relaxed. And based on that, we should be able to see if our data, the epsilon values for the maximum wavelength of absorption on our UV-Vis spectrum, matches that category appropriately or not. So what you need to do is convert your data on your UV-Vis to have the epsilon values showing. Look at that wavelength of highest absorption. Look for the peak. What is the epsilon value at that peak? Does it fit into the category of Laporte forbidden? Or is it Laporte relaxed? Or are you seeing one that is not even spin allowed? Maybe you don't see much of a transition at all. Then you might have no spin allowed transitions. That would be something 1 to 10 molar per molar per centimeter, 100 per molar per centimeter tells you Laporte forbidden, and then 1,000 to 10,000 would tell you Laporte relaxed.